Is the screen visible? Anyone reply?
Yes, sir.
Thank you.
Yes, sir.
Yes, sir.
Thank you. We'll start the class. So in the yesterday's class, I was solving this second problem. Part of it was completed, and today we'll uh, complete the full solution, and we'll move for the next problem. Okay. Just go through it. A post-tension pre-stress concrete beam of 50 meter span is subjected to a transfer pre-stress force of 9.38 meganewton. Transfer of force is at 28 days. The age of transfer is given as 28 days. Profile of the cable is parabolic with eccentricity at midspan as 1100 mm. And it has asked to find the losses of pre-stress and the jacking force required. The beam is subjected to live load. Live load is given 24 kilonewton per meter. And it is said that the jacking is done at both ends of the beam. Okay. And the data required for the calculation, the relevant data required for the calculation is given. All the constants, okay, the material properties, okay, sectional properties, everything is given. Just you need to calculate different types of losses. Adding all together, you will get the total loss, and you can calculate the percentage loss. Okay. So yesterday we have calculated two losses, that is loss due to elastic deformation and loss due to shrinkage. We have calculated, correct? Now here you can see the type of PSC beam is a post-tension PSC beam it is. Okay. So type of losses depends on type of the pre-stress concrete member, correct? For post-tension it will be different. For pre-tension member it will be different. Okay. Now for elastic deformation and shrinkage we have calculated. Next we will calculate for creep. Okay, loss due to creep. Third one, loss due to creep. Write down. Loss due to creep. Okay, loss due to creep we will calculate. What is the formula for loss due to creep? Let me go to the formula. Yes, here we have the formula for calculating loss due to creep. Okay. So there are two different formula. When creep coefficient is given, there is formula to calculate the loss, and when ultimate creep strain is done, so using this epsilon CS, FC, and ES, we will calculate the loss due to creep. Okay. So in this problem, the creep coefficient is given, correct? In this problem, creep coefficient is given. How much it is given? It is 1.2. So using creep coefficients, what is the formula? Pi into FC into M. Let me take that formula. Now, loss due to creep is given by loss due to creep is given by using creep coefficient. The formula is pi into FC into M is the formula, correct? Where pi is creep coefficient, which is given as 1.2 in the problem, correct? Then what we need? We need the value of FC. What is the meaning of FC? What is the meaning of FC? Stress in concrete at the level of steel. Okay, FC is nothing but stress in concrete at the level of steel. Okay, now write the side line as calculation of FC. Okay, for calculating FC also we have the formula, correct? Yes, here we have the formula to calculate the FC. Okay, let me copy this formula. FC is equal to P by A plus PE by I into E minus M by I into E. Okay, FC is equal to P by A plus PE by I into E minus M by I into E. This is the formula. Okay. Now, pre-stressing force, is it given? Pre-stressing force. Let me check. Original pre-stressing force, it is given as 9.38 meganewton. Okay, here 9.38 into 10 power 6 Newton. Okay, P is equal to 9.38 into 10 power 6 Newton. And cross-sectional area of the member. Cross-sectional area of the member, is it given? Area of concrete, here it is given 9,47,100 mm square. Okay, area is given as 9,47,100 mm square. Okay, then what else is required? Then eccentricity is required, no? Eccentricity is required and moment is also required. Moment is also required. Now we will calculate the moment. Okay, moment due to the live load and the dead load we have to calculate here. Okay, moment due to live load and the dead load. So first we calculate the live load, dead load, and live load is given in the problem. We add both the values, you will get the total load. Okay, so the moment of the total load will be this M. Okay, now dead load of the beam is equal to dead load of beam is equal to what is, how we will calculate that dead load or sulfate? How will calculate? Area multiplied by density, correct? Area, cross-sectional area multiplied by density will give dead load of the beam. Okay, so cross-sectional area is 99,47,100 mm square. Okay, it is in terms of mm square. Convert it into meter square. So 10 power minus 3 whole square. Now it is converted into meter square. Into density is 24 kilonewton per meter cube. Correct? So by this you will get the dead load intensity of the beam. How much you will get? Please calculate. Please calculate the answer. If you calculate, please check the answer. 22.73 kilonewton per meter. Okay. Please cross check the answer. All of you calculate and cross check the answer. If you are getting any different answer, let me know. Okay. Then live load on the beam is given. Correct. Live load on the beam is given in the problem only. How much it is given? Live load, it is 24 kilonewton per meter. 24 kilonewton per meter. Okay. Live load on beam is equal to 24 kilonewton per meter. Okay. Therefore, the total load is, add both the values. Check the answer, 46.73 kilonewton per meter. Okay, will be the total load. Okay, which is W. Okay, Now we can calculate the moment. Therefore, moment M is equal to W L square by 8 is equal to 46.73 into length of the beam. How much it is given? Length of the beam. Length of the beam. Just check where it is given. Length of the beam. As 50 meter span. Length of the beam is given as 50 meter here, correct? So L is 50 meter, 50 square by 8. 50 square by 8. If you calculate the answer, you will get 14,603.12 kilonewton meter. Okay, therefore M is equal to 14,603.12 into 10 power 6 Newton millimeter. Okay, this is moment due to dead load and live load. Okay, moment due to dead load and live load. Okay, now we have to calculate the value of FC. Okay, we have to calculate the value of FC. FC, as I said, FC is nothing but stress in the concrete at the level of steel. Okay, stress in the concrete at the level of steel is called as FC. But in this particular problem, the cable profile is parabolic in nature, correct? The cable profile is parabolic, having 1100 mm eccentricity at the center and 0 eccentricity at the support. Okay. So FC is stress in the concrete at the level of steel. Okay, but here the level of steel is not constant. Okay, it is changing with the length of the beam. Correct? The level of the steel is not constant. It is parabolic in nature. The level of steel is changing with the length of the beam. Okay. So now the question is where exactly we have to calculate the stress in concrete. Okay, that is the question. Correct. So in case of parabolic cable, what we will do is we will calculate FC at the midspan. Then we'll also calculate FC at the support where eccentricity is 0. Knowing both the stresses at support and the center, we will calculate the average FC. We will calculate the average FC. Okay. Now what we have to do is we have to calculate FC value. FC value at support where eccentricity is 0. FC value at midspan where eccentricity is 1100 mm. Okay. Knowing both FC values, we can calculate the average FC. Okay. Average stress in the concrete. Okay. Now I'll rewrite the above equation as FC support is equal to FC support is equal to P by A then plus PE by I into E plus PE support eccentricity at support by I into E support. Okay, E support minus M by I into E minus moment at support by I into E support. Okay. Now we are calculating stress at the support. Okay. Therefore, we have to substitute the values corresponding to the support only. Okay. Therefore, we need to substitute eccentricity at the support and moment at the support. Moment at the support. Okay. Now eccentricity at support is how much? Eccentricity is support how much? It is 0 only. There is no eccentricity at the support. E support is 0. Okay. It is 0. Okay. Therefore eccentricity at support is 0. Even moment at the support is also 0 because the beam is carrying a total UDL of how much? Total UDL of 46.73 kilonewton per meter. Okay, 46.73 kilonewton per meter. If you calculate moment at the support, it will be 0 only because it's a simple support. The beam is provided with simple support. At simple support, the moment will be 0. Moment at support will be 0. There will be moment at the mid span or any other span. Okay, at supports moment will be 0 and moment at support is also 0. Therefore, the above equation can be rewritten as FC support can be written as P by A plus eccentricity at support is 0. So this term becomes 0 minus moment or eccentricity in the second term, that is also 0, 0. So only FC support is P by A. Okay. So P precessing force is given 9.38 into 10 power 6, 9.38 into 10 power 6 divided by area of cross section. How much it is given? 94,000, 9,47,100. 9,47,100. Okay. By this, you will get stress in the concrete at the level of steel at support. Okay. Support is equal to 9.9 Newton per mm square. Please cross check the answer. Don't simply listen to the class. All of you solve the problem. Okay. In the same way, we need to calculate stress in the concrete at the level of steel at midspan. Okay, FC midspan. Okay, FC. Similarly, FC midspan can be calculated. How? It is P by A plus PE midspan divided by I into E midspan. Okay, minus M midspan divided by I into E midspan. Okay. Now eccentricity at midspan. How much? It is given in the problem. 1100 mm square here. 1100. Sorry, mm. 1100 mm. Okay. And moment at midspan. We have already calculated it before. That is WL square by 8. That is 14,603.12. 12 into 10 power 6 Newton millimeter. Okay. Now you can substitute everything to get the stress at steel at the midspan. FC midspan is equal to P by A value already we have calculated in the previous calculation. It is 9.9. Only to substitute once again. 9.9 plus, okay, P into E midspan. P is 9.38 into 10 power 6. 9.38 into 10 power 6 into 1100 divided by moment of inertia. How much it is? Moment of inertia. Just go through the problem. It is 6224 into 10 power 8 mm4. Okay, 6224 into 10 power 8 into 10 power 8 into again E midspan into 1100 minus moment at midspan, it is 14,663.12 into 10 power 6 divided by moment of inertia 6224 into 10 power 8 into eccentricity at midspan 1100. Okay, calculate the answer. You will get the stress at midspan. Okay, calculate the answer. Please check your answer. It is 2.33 Newton per mm square. 2.33 Newton per mm square. Okay. Now we can calculate average stress. Average stress calculation is, let me write the diagram for calculation of the average stress. Assume this has midspan. Okay. Now we have calculated stress at support. How much it is? 9.9 Newton per mm square. Correct? 9.9 Newton per mm square. 9.9 at the support. Okay. And stress at the midspan is 2.33 Newton per mm square. 2.33 Newton per mm square. Okay. Now here in the problem, the cable profile given is parabolic. Therefore, the nature of variation of stress will also be parabolic only, like this. Okay. Now we have to calculate average stress from this diagram. Okay. It is not like average of both numbers. Okay. It is not like average of both numbers. It is average of both numbers when the nature of variation of stress is linear. Okay. Here the cable profile is parabolic. So nature of variation of stress is also parabolic in nature, like this. Like this. Okay. Now for this diagram, you need to calculate average stress. Okay, you need to calculate average stress. Okay. Now to calculate the average stress, let me write the horizontal here. Okay. See, up to this point, the average stress is how much? It is 2.33. Okay. Now what we have to do is we have to calculate average stress for this parabolic portion. Okay. We have to calculate average stress for this parabolic portion. So how to calculate this average stress? Let me write the calculation below. Average FC. Average FC is equal to, see, up to this point it is 2.33. Average stress is 2.33. 0.33 plus now we have to calculate average stress for this portion. We have to calculate average stress for this portion. Then for it is a parabola, as you can see, it is a parabola. For parabola, average stress is calculated as 2/3 of, okay, 2/3 of this value plus this value. Here it is 0. Then total height is 9.9. 9.9 minus 2.33. If you do, how much you'll get? You will get some value here. Okay. This is 9. So this height will be 9.9 minus 2.33. Okay. So average stress for this hatched portion by blue line, okay, is calculated as 2/3 of this height. Okay. 9.9, okay, 9.9 minus 2.33. Okay, 9.9 minus 2.33. Okay, 2/3 of this portion will give the average stress. Okay. Now FC is equal to, if you calculate the FC, you will get average FC as 7.37 Newton per mm square. Okay. By calculating, are you able to understand this calculation, students? See, by calculating 2/3 of this height. Okay, by calculating 2/3 of this height of this parabola, okay, the parabolic variation of the stress is converted into a average stress like this. Okay. Okay. So 2.33 plus this average stress will give total average stress of 7.37 Newton per mm square. Okay. 7.37 Newton per mm square is the average stress, average FC value for this figure. Okay. So if you have got any doubt in this calculation, you can ask students. Okay. Very simple calculation. At the support we got 9.9, at the midspan we got 2.33. Okay. So up to 2.33, nature of variation of the stress is same only. Okay. The average stress is 2.33 only. After 2.33, nature of variation is parabolic. So for parabolic, we have to convert it into the rectangle. Means we have to convert that parabolic variation into constant variation. Means we have to convert that parabola into rectangle. How to convert that? 2/3 of this height. Okay, 2.33 constant plus this height, 2/3 of this height will give conversion of this variation of stress into a rectangle. Okay, a constant stress or an average stress throughout the length, 7.37 Newton per mm square. Okay, so this is parabolic variation. Now we got the value of FC. Okay. Creep coefficient pi is 1.2, FC just we have calculated, it is 7.37. Then what else is required? We require modular ratio to calculate the loss. Correct? Modular ratio to calculate. What is modular ratio? Modular ratio M is given by the ratio of Young's modulus of steel to that of Young's modulus of concrete. Okay. Young's modulus of steel and concrete is given in the problem. Just see how much it is given. See, Young's modulus of steel is 210 gigapascal and 38.2 gigapascal. as Young's modulus of concrete. Okay, 210 by 38.2. So if you calculate, you will get 5.5 as modular ratio. Now every parameters are known. You can calculate loss due to creep. Therefore, loss is equal to loss is equal to pi into FC into M. Pi is 1.2, FC is 7.37, 1.2 into 7.37 into modular ratio 5.5. By this you'll get loss due to creep. Please calculate and check the answer. 48.64, okay, Newton per mm square is the loss of stress due to creep. Okay, so this completes the calculation of loss of stress due to creep. Okay, so any doubts you can ask before moving to the calculation of the next type of loss. Next type of loss, what we have to calculate is loss due to relaxation of stress in steel. Okay, the serial number is 4D. Okay, loss due to relaxation of steel, relaxation of stress in steel. Okay, how we will calculate loss due to relaxation of stress in steel? It is calculated as loss due to relaxation of stress in steel is calculated as percentage of initial pre-stress. Percentage of initial pre-stress. Okay, here you can see loss due to relaxation. No? Yes, here it is calculated as loss is equal to percentage of initial pre-stress. Initial pre-stress is given. Okay, initial pre-stress is given in the problem, and loss of uh, stress due to relaxation is also given. That percentage is also given. Okay, initial pre-stress, how much it is given? Just see. Pre-stressing force is given. Area of concrete is given. Area of steel is given. I think stress we have to calculate. Yes, it already we have calculated. No, here at the beginning. At the beginning only we have calculated initial pre-stress 1050.4. Okay, so initial pre-stress is 1050.4, and loss due to relaxation of steel is 2%. Okay, so 2% of this 1050.4 is the loss due to relaxation of steel. Okay, therefore here 2% of, below line you write percentage of relaxation of steel is given as 2%. Correct? Huh? Is given as 2%. Therefore, loss is equal to 2% or 2 by 100. Okay, 2 by 100 of initial pre-stress 1050.4. Therefore, loss is equal to, it's a very simple calculation. 2 by 100 into 1050.4, if you calculate, you will get 21 Newton per mm square. Cross check the answer. 21 Newton per mm square. So to this loss due to relaxation of steel is over. Okay. Very simple calculation. Next type of loss due to anchorage slip, correct? Loss due to anchorage slip. See, for post tension member, all the losses will come into picture. Okay, provided the bars are stretched one by one for calculation of loss due to elastic deformation. Okay, these five will definitely come. Five losses, that is loss due to shrinkage, creep, and relaxation of stress in steel, loss due to friction. Okay, loss due to anchorage slip. All five losses will definitely come for post tension member. Post tension member. Even this loss of pre-stress due to elastic deformation will also come when the cables are pulled one by one. So in this problem, cables are pulled simultaneously, there is no loss. Okay. Next, we will calculate loss due to anchorage slip. Okay. Fifth one, loss due to anchorage slip. Loss due to anchorage slip. Anchorage slip. Okay. Now how to calculate loss due to anchorage slip? What is the formula? So using this formula, loss is equal to delta by L into ES. Okay, where delta is amount of slip, L is length of the beam, and ES is the Young's modulus of steel. Okay, let me take that formula. Loss is equal to delta by L into ES. Okay, where delta is amount of slip. It is given in the problem, correct? Amount of slip, how much it is given? It is given as 2.5 millimeter per anchorage. Okay, 2.5 millimeter per anchorage. Okay. Now for one anchorage means on one side 2.5 millimeter is the slip. Okay, so on both the sides it will be 5 millimeter. Correct? Now delta is equal to 2.5 millimeter, 2.5 millimeter per anchorage for one side. Okay. So for both the sides, it will be total 5 mm. Okay, let me show it in the calculation. Therefore, loss is equal to and length of the beam is given as 50 meter. So delta we are substituting in terms of millimeter. So length also you take with the same unit, 50 into 10 power 3 millimeter. Okay. Young's modulus of the steel is given. It is 210 into 10 power 3. We can just substitute and get the answer. Therefore, loss is equal to 2.55 into 2. Don't forget. Okay. For one anchorage. Okay. The anchorages are there on both sides of the beam here. Okay. He clearly says that jacking is done at both ends of the beam, means anchorages are there on both the ends. Okay, for one anchorage 2.5 mm is the slip. For two anchorages multiply by 2. Okay, multiply by 2. So this is because two number of anchorages. Okay, into 2 into divided by L, 50 into 10 power 3 into Young's modulus of steel 210 into 10 power 3. Okay, by this we'll get loss due to anchorage slip. Okay, we'll get loss due to anchorage slip. How much you'll get? Check the answer. It is 21 Newton per mm square. 21 Newton per mm square. Okay. Now we have calculated five losses. One more loss is remaining. One more calculation of the loss is remaining. What is that? It is loss due to friction. Last one. Loss due to friction. Okay. Loss due to friction. Okay. Now I'll go to the notes. Loss due to friction. Let us see what is the formula to calculate the loss due to friction. Yes. Here we have the formula. Loss is equal to P naught into mu alpha plus Kx. Okay. So this terminology, this terminology is given in page number 25 of IS 1343. Let me check it. Code books now. Yes, this is only the code book. Yes, it is 33. Page number 33, not 25. Here we have that formula. Okay. So actually this Px is a stress at a distance x. Okay. Is equal to P naught into e power minus mu alpha plus Kx. Okay. And this formula, same formula I written, and I have simplified, and after simplification finally I got the expression for loss of pre-stress. That is, loss is equal to P naught into mu alpha plus Kx. Okay. So you can just open page number 33 of the codebook. This mu alpha plus Kx is there. Okay. And P naught is also there. Okay. Excluding this e power. So this formula will be P naught into mu alpha plus Kx. Okay. P naught into mu alpha plus Kx. Okay. So just by referring this formula, you can write the expression for the loss. Okay, because the terminologies are same only, same. No? Therefore, here I'll take this formula. P naught loss is equal to P naught into mu alpha plus Kx. Only the e power minus will not come. Okay, rest of the term will come as it is. Correct? Into mu alpha plus Kx. So loss is equal to P naught into mu alpha plus Kx. Loss is equal to loss due to friction is calculated as P naught into mu alpha plus Kx. P naught into mu alpha plus Kx. Okay, using this formula, we will calculate loss due to friction. Okay, now P naught is nothing but initial pre-stress, where P naught is initial pre-stress that we have already calculated at the beginning only. How much it is? It is 1054 or 53. 1050, I think. As it is 1050.4 Newton per mm square initial pre-stress. 1050.4 Newton per mm square. Okay. Then mu is nothing but coefficient of friction. Okay, mu is nothing but coefficient of friction, and it is given in the problem. Okay, and it is given in the problem. Let us see coefficient of friction. It is 0.25. Let me take the same value 0.25. Mu is equal to, it is given as 0.25. Okay. Then what we need? We need the value of alpha. Correct? We need the value of alpha, where alpha is the cumulative angle which is calculated as per this note. Okay, please listen carefully. Please listen carefully. See, calculation of alpha I am explaining now. See the cable profile. If the cable profile given in the problem, if it is a parabolic cable, we have to calculate slope as 4e by L. Okay, and this slope is calculated is required for calculation of the alpha only. Okay, that's why we are calculating slope. Okay, for parabolic cable, the slope is calculated as 4e by L. If the cable given is linear, cable given is having a linear profile, then slope is calculated as 2e by L. Okay, now this is how we calculate the slope. Okay, depending upon the cable profile. Next, coming to the calculation of alpha and x here. Okay, here we have one more terminology, x, correct now? Coming to the calculation of alpha and the x, if the cable is pulled from only one end, okay, one end, then alpha is calculated as 2 into slope and x is taken as length of the beam. Okay, if the cable is pulled from both the ends, then alpha is equal to the slope whatever you have calculated based on the cable profile, and x is taken as L by 2, total length of the beam divided by 2. So in this case, in our problem, okay, in our problem, he clearly says that, okay, he clearly says that the jacking is done at both ends of the beam, means cable is pulled from both the ends of the beam. So we have to utilize this second condition. Okay, that is alpha is equal to slope and x is equal to L by 2, and this slope is calculated based on the cable profile. Okay, for parabolic profile it is 4e by L, for linear profile it is 2e by L. So in our problem we have the parabolic cable, so slope is calculated as 4e by L. Okay, first you calculate the slope. I hope you are following the lecture. First you calculate the slope. for parabolic cable or parabolic cable, the slope is calculated as 4E by L. Okay, 4 into 1100 divided by L is length of the beam 50 into 10 power 3. Okay, eccentricity we are substituted in terms of mm, so length of the beam also in terms of mm. If we calculate, it is 0.088. Now we have calculated the slope. Okay, then coming to the calculation of alpha. Okay, as cable is pulled from both ends, okay, the alpha is calculated as slope divided by 2. Slope divided by 2. Correct? Sorry, alpha is directly taken as slope. Sorry, directly taken as slope value. Okay, if it is pulled from only one end, 2 into slope. Okay, so it is pulled from both ends. So alpha is equal to directly whatever the slope value we have, that is the value. Slope is 0.088. 0.088. Then coming to the value of calculation of the x is taken as L by 2 if the cable is pulled from both ends, and x is equal to L by 2. Okay, L by 2. L is 50 meter divided by 2, that is 25 meter. Okay, that is 25 meter. One more important thing, very important things. So in this formula, no, in this formula, x distance is there, no, it should be substituted in terms of meter. Okay, it should be substituted in terms of meter, and you will get the answer in terms of Newton per mm square. In that way, this formula is derived. Okay, that is how this formula is derived. Okay, remember this point. X should be substituted in terms of meter. That is why I calculated it in terms of meter only. Okay, so in the bracket you can write a small note. It should be in mm. It should be in mm. Okay, now all the values are known. Just to calculate the loss. Therefore, loss of pre-stress due to friction is given by P naught 1050.4 into 0.25 is the mu value. Alpha value is 0.088 into 25. Plus kx is there, no? K is given. Okay, k is given. That is a oval constant. That is given in the problem. 0.0015 per meter. Oval coefficient of oval constant or wave effect. It is also called as wave effect constant. Okay. So P naught into mu alpha plus kx. Plus kx. K is given as 0.0015 into x is 25. So by this you will get the loss due to friction. Okay. Calculate the answer and secure answer. It is 62.5 Newton per mm square. Okay, 62.5 Newton per mm square. To this, calculation of loss of pre-stress due to friction is over. Okay. To this, we have calculated all the types of losses which will come under post-tensioned concrete beam. Correct. Now you can calculate the total loss. Okay. Total loss is the sum of loss due to elastic deformation, loss due to shrinkage, loss due to creep, then loss due to relaxation of stress in steel, loss due to Anchorage slip, and loss due to friction. Okay. Therefore, the total loss of pre-stress, total loss of pre-stress is equal to we add one by one. There is no loss due to elastic deformation, loss due to shrinkage is 28.43. Okay, plus 9.9. Then sorry, 28.23 plus 48.64 plus 21 plus 21 plus 62.5. Adding all together, loss of stress due to elastic shortening is 0. 28.43 plus 48.64 plus 21 plus 21 plus lastly 62.5. By this we'll get total loss, that is 181.56 Newton per mm square. 181.56 Newton per mm square. Okay, we can also calculate the percentage of loss. Percentage of loss is equal to total loss is 181.56 out of initial pre-stress was how much? 1050.4. 1050.4. So in 1050.4, 181.56 Newton per mm square is the loss into 100 will give percentage of loss. It is 17.28%. 17.28%. Okay. So to this calculation of the total loss and percentage loss is over. There is one more question at the last. What is that question? Just go through it. It is he asked determine the loss of pre-stress that we have already determined now and find the jacking force required. Okay, find the jacking force required so as to overcome all the losses. Okay, jacking force required so as to overcome all the losses. Okay, now write the side line as jacking force required. Calculation of jacking force required. Jacking force required. Calculation of jacking force required. Okay. Jacking force required so as to overcome all these losses. Okay. See, if we apply the jacking force with respect to the jacking force in such a way that it will cause 1050.4 Newton per mm square, in that there will be a loss of 181.56 Newton per mm square. Okay. Now to calculate jacking force required to overcome all these losses, you need to take into consideration of this loss and you need to calculate the jacking force required. Okay. Therefore, the jacking force is calculated as initial pre-stress plus total loss into cross-sectional area of the cable. Okay. If you calculate the jacking force, okay, considering the losses, then there won't be any further losses. Okay. So required stress we can achieve. Required stress of 1050.4 we can achieve. That is the meaning. Okay. Initial pre-stress is 1000. 50.4 plus total loss is 181.56 into area of cable. It is given in the problem. Area of cable. It is 8930 mm square. Okay, 8930 mm square. 8930. Okay, calculate it and check the answer. It is 11 into 10 power 6 Newton. Okay, therefore jacking force is equal to 11 into 10 power 6 Newton. Okay, or 11 mega Newton. So this completes the problem. Okay, any doubts in any steps you can ask students before moving on to the next problem. So problems are easy. You need to remember all the relevant formulae. Okay, then you can calculate the things properly.
Sir, once again repeat the step of loss due to friction. Sir.
Loss due to friction, huh? Okay.
Yes, sir.
See, this loss due to friction is calculated as loss is equal to P naught into mu alpha plus Kx. Okay. If you are if you face any difficulty in remembering this formula, I said no, I shown in the code book. So you refer this formula. Only if you skip this e power minus rest formula, if you write as it is here in the LHS loss, okay, loss is equal to P naught into mu alpha plus Kx. You can remember in that way. So using this formula, we'll calculate the loss due to friction. Okay. So where P naught is initial pre-stress that we have calculated in the beginning of the solution, correct? Here, loss of pre-stress, initial pre-stress in the cable is equal to the initial pre-stressing force divided by area of cable. Using that formula, we have calculated, we got it as 1050.4 Newton per mm square as initial pre-stress. P naught is known. Okay, that I have written here. Okay, and mu is coefficient of friction, that is also given in the problem. Coefficient of friction. Here it is given 0.25. That also I have written. Then next comes the alpha. Okay, next comes the alpha. For calculation of the alpha, here in the notes I have given the guideline. Okay, so you just refer this note so that we can understand how to calculate this alpha. Okay, to calculate this alpha, initially you need to calculate the slope. Okay, and the calculation of the slope depends on cable profile, whether it is linear or parabolic or straight. For straight cables, slope will be 0. Okay. For parabolic cable, slope is calculated as 4e by L, and for linear cable, means triangular profile cable, it is calculated as 2e by L. Okay, so as we are having parabolic profile, I'll calculate the slope by using this formula 4e by L. Okay, so I have calculated the slope using 4e by L formula. I got it as 0.088. Okay, knowing the slope or by using the slope, we'll calculate the alpha value. Okay, and calculation of the alpha depends on whether the cable is pulled from only one end or whether it is pulled from both ends. Okay, so in this problem, he said that the cable is pulled from both ends. Okay, cable is pulled from both ends. Okay, so with respect to the second case, cable pulled from both ends, you need to calculate alpha as equal to slope. Alpha is taken as equal to slope. Slope we have calculated as 4e by L, and x is taken as L by 2. Okay, here you can see alpha is equal to slope, whatever we have calculated 0.088, and x is equal to L by 2. And important thing, this x should be substituted in terms of meter. Okay, this formula is derived in such a way that if you substitute the x in terms of meter, you will get the loss in terms of Newton per mm square. Even the initial stress should be substituted in terms of Newton per mm square. Okay, only the x should be substituted in terms of meter. Remember this. Okay, x is equal to taken as L by 2 if the cable is pulled from both the ends. Okay, x is equal to L by 2, alpha is equal to slope, whatever you calculated by this formula. Okay, instead of saying cable pulled from both ends, if he says it is pulled from only one end, you need to use this formula. Alpha is equal to 2 into slope and x is equal to L formula. Okay, now we got slope, the alpha and x value. Okay, alpha and x value. K is nothing but Wobble constant or the wave effect, constant of the wave effect, that is given in the problem only. K is equal to 0.0015 per meter. That is given in the problem. So K I have taken as 0.0015. Substituting all the values, we will get the loss due to friction. Understood, Kishore? Any doubts still?
No, sir.
Okay, thank you. Now we'll move on to the next problem. Please note the third problem. Are you able to read this problem? Somewhat blur it is. Are you able to read the problem?
Yes, sir.
Please, anyone reply?
Yes, sir.
Okay. I have to read this problem. Meanwhile, I'll write the diagram. Okay, go through the problem. A post-tensioned rectangular beam 300 by 600. Okay, cross section is 300 by 600. I have written in the diagram. In section is pre-stressed with initial pre-stress of 950 Newton per mm square. Initial pre-stress is given. Just write it below. Given data. Initial pre-stress is 950 Newton per mm square. And he says that there are 4 straight cables of each area 250 mm square. Okay, 250 mm square. The cables are situated at 100 mm from soffit. Okay, there are 4 straight cables. 1, 2, 3, 4. Okay, there are 4 straight cables situated at 100 mm from soffit. Okay, this is the cross section. This is the longitudinal section I have written. Okay, in the longitudinal section, you can see length of only one cable. Okay, because all the cables are at same level, you can see only length of one cable. Just that is why I written only one cable along the length of the beam. That is at a distance of 100 mm from soffit of the beam. Okay, and area of each cable is given. Okay, of each area 250 mm square. Area of each cable. Area of each cable is equal to 250 mm square. Okay. Determine percentage loss of pre-stress due to concrete. Okay. Assume the following: shrinkage strain in concrete is given. Okay. Then modular ratio is given. Ultimate creep strain of concrete is also given. And he says that the cables are pulled one by one. This you need to remember, note. Okay. He says that the cables are pulled one by one, and it is a post-tensioned rectangular beam. Okay. Whenever if you start solving problem on loss of pre-stresses, you should see whether the beam is post-tensioned or pre-tensioned. Okay, and you should also see whether the cables are pulled one by one or simultaneously, or jacking is provided at only one end, both end. All the things you need to see, and you need to solve the problem accordingly. Okay, because the calculation varies depending upon the condition. Okay, depending upon all these conditions. Okay, depending upon the type of beam, whether it is pre-tensioned or post-tensioned, depending upon the jacking, whether it is at one end or both ends. Okay, and the type of pulling of the cables one by one or simultaneously. So based on all these conditions, the calculation will vary. Okay, so we have to determine percentage loss of pre-stress. Okay, so we'll calculate the losses one by one. We'll calculate the losses one by one. First one is loss due to elastic deformation. Okay, see here you can see initial pre-stress is given, and the area of each cable is also given. So you can calculate the pre-stressing force in the cable. Okay, therefore pre-stressing force in cable. Therefore pre-stressing force in cable is equal to stress multiplied by cross sectional area, that is 950 into 250. Okay, the answer is 237.5 into 10 power 3 Newton. Check the answer. It is 237.5 kilonewton. Okay, now we'll start calculating the losses one by one. First one is loss due to loss due to elastic deformation. Elastic deformation. Loss due to elastic deformation. See here in this problem, he says that the cables are pulled one by one. Okay. If the cables are pulled one by one, there will be loss due to elastic deformation. In the previous problem, he said that cables are stretched simultaneously. Okay. Cables are stretched simultaneously. Okay. Jacking is done on both the ends of the beam. Okay. See, if the cables are pulled one by one, specifically it will be given in the problem, like cables pulled one by one. Okay. If the condition of pulling of the cable is not given, it is understood that it is stretched simultaneously. All the cables are stretched simultaneously. Okay. So here it is specifically said the cables are pulled one by one. Okay. If the cables are pulled one by one, there will be loss due to elastic deformation for post-tension concrete beam. Otherwise, it will be 0. Why? I have explained in the beginning only, in the theory class only. Okay. Now, below you write a sentence. In post-tensioned beam, in post-tensioned beam, if cables are pulled one by one, then there is loss due to elastic deformation. Then there is loss due to elastic deformation. Elastic deformation. Okay, you have to calculate the loss due to elastic deformation. What is the formula to calculate the loss due to elastic deformation? Let us see. Yes, here we have the formula. Loss due to elastic deformation of the concrete in pre-tensioned beam and in post-tensioned PSC beam. It is calculated using M into FC formula only. Okay, M into FC formula only. Okay. See here I written. If the cables are pulled one by one, there is loss of pressures and it is calculated as loss is equal to M into FC. Okay. Now loss is equal to M into FC. Okay, what is M? M is modular ratio, which is the ratio of Young's modulus of steel to that of concrete. It is directly given in the problem. Modular ratio, it is 6. M is equal to 6. M is equal to 6. Okay. And we need to calculate FC. What is FC? Stress in concrete at the level of steel. Okay, stress in the concrete at the level of steel. What is the level of steel? See, the cable profile is straight. Okay, the cable is having same level throughout its length. Okay, so only in a single shot you can calculate the FC value, not and it is not a difficult task. If it is a parabolic cable, you need to calculate FC at the support mid span, then you need to calculate the average FC that we have practiced in the previous problem, correct? So here, as the cable profile is straight here, in a single shot, you can calculate the average FC. Okay, for straight cable, right? We know that, and FC is equal to, what is the formula? FC is equal to, we have the formula here, P by A plus PE by I into E minus M by I into E. P by A plus PE by I into E minus M by I into E. Okay. Force P is given, correct? Force P is given. Sorry, we have calculated, that is 237.5 kilonewton. P is equal to 237.5 kilonewton. 237.5 into 10 power 3 Newton. Then area of cross section, we can calculate. It is 300 by 600. Don't substitute the area of cable here. Okay, it is area of section. Okay, area of cable will come into picture only while calculating the pre-stressing force. Okay, so 300 by 600 is the area. 300 by 600. If you calculate, it is 180,000 mm square. Okay, area of the cross section. Then eccentricity. What is the value of eccentricity here? Tell me, students. Anyone? Eccentricity, is it given in the problem? It is not given, correct? Nowhere he mentioned the eccentricity, but the location of the cable is given. Location of the cable is given as 100 mm from the soffit. Okay, here I mentioned 100 mm from the soffit. Okay, but eccentricity is not given. That you can calculate. You can calculate. If it is not given, you can calculate, because the location of the cable is known. You can calculate the eccentricity. Okay, what is eccentricity? Distance between the neutral axis or centroidal axis to that of centroid of the cable is called as eccentricity. Okay, so this length is how much? This length is, overall depth is 600. 600 divided by 2, 300. Okay, 300. Okay, distance of neutral axis from bottom fiber is 300. Distance of bars, cables from bottom fiber is 100. So eccentricity, distance between the neutral axis and the cable will be 300 minus 100. So it will be 200 mm. Okay, it will be 200 mm. Let me read the calculation here. E is equal to 300 minus 100, that is 200 mm. Okay, 200 mm. Then what else is needed? Moment of inertia is needed, no? I. Moment of inertia is needed. I is equal to BDQ by 12 for rectangle. B is 300 into depth is 600 cube divided by 12. Depth is 600. So the answer is 5.4 into 10 power 9 mm4. Okay, 5.4 into 10 power 9 mm4 moment of inertia. Then what else is needed? We need the moment due to dead load and the live load. Okay, so in the problem, nowhere the loading on the beam is given, correct? Pre-tension rectangle beam. So the load is not given. Live load on the beam is not given. So as a live load is not given, we will ignore this dead load moment also. We will take m is equal to 0. Okay, taking m is equal to 0 because live load is not given. Okay, and dead load moment is neglected. Neglect dead load. Okay, now you can calculate the value of FC. FC is equal to P is 237.5 into 10 power 3 divided by cross sectional area 180,000 plus 237.5 into 10 power 3 into eccentricity 200 due to the moment of inertia 5.4 into 10 power 9. Again eccentricity 200 minus m by I. M value we are taking as 0, so that term becomes 0. Therefore, Fc is equal to, please calculate the answer and check your answer. It is 3.07 Newton per mm square. 3.07 Newton per mm square. Okay. Now we have calculated Fc. See, in the problem, what is said is the cables are pulled one by one. Okay. First cable is pulled and anchored. After that, second cable is pulled and anchored. Similarly, third and fourth cable. That is what the pre-stressing is done in this post-tension concrete beam. Okay. So if the cables are pulled one by one, you need to calculate the loss of pre-stress due to elastic deformation in each and individual cable separately. Okay, you need to calculate loss of stress in each and every cable separately. Okay, if the cables are pulled one by one. If the cables are pulled simultaneously, there won't be any loss. Okay, if the cables are pulled simultaneously and anchored simultaneously, okay, in that case, the loss of the initial pre-stress will be taken considering the loss only. Okay, therefore we are not going to calculate the loss of pre-stress if the cables are stressed simultaneously. Okay, only we need to calculate if the cables are pulled one by one. Okay, now what I will do is I will calculate loss in each and every cable separately. First one, okay, if cable 1 is pulled and anchored, then loss in cable is 0. Okay, why it is 0? See, when the cable 1 is pulled and anchored, okay, then whatever the actually loss happens, that loss is the initial pre-stress is considered after that loss only. Okay, after that loss only. Okay, initial pre-stress is calculated after the loss only. Okay, therefore loss in cable is 0. Cable 1 is 0. Loss in cable 1 is 0. Then after the cable 1 is being pulled and anchored, then what is done is cable 2 is pulled and anchored. Okay, cable 2 is pulled and anchored. In that case, loss in cable 2 is 0, but loss in cable 1 is m into Fc. Okay, m into Fc formula. That is m is modular ratio is 6 and Fc is 3.07. 6 into 3.07. That is 18.42 Newton per mm square. Okay, I hope you are understanding. See, so this is what the cross section we have, and there are 4 cables. Okay, assume that first cable is pulled and anchored. First cable is pulled and anchored. So in this case, there will be loss, but the initial pre-stress is calculated in the bar after the loss only. That after the elastic deformation of this cable one only. Okay. Next, what happens? The second cable is pulled and anchored. Okay. Second cable is pulled and anchored. When the second cable is pulled and anchored, the loss in cable 2 is 0. Okay, but there will be loss in cable 1 because of pulling of cable 1. Okay, because of pulling and anchoring of cable 2, there will be loss in cable 1, that is M into Fc. If cable 3 is pulled and anchored, okay, if cable 3 is pulled and anchored, loss in cable 3, okay, loss in cable 3 is 0, but there will be loss in cable 2 and 3. There will be loss in cable 2 will be equal to M into Fc, that is 6 into 3.07, that is 18.42 Newton per mm square, and there will also be loss in cable 1, same value M into Fc, that is 18.42 Newton per mm square. Okay, then similarly you need to do the calculation for cable 4. When the cable 4 is pulled and anchored, then loss in cable 4 will be 0. Loss in cable 4 is equal to 0. Loss in cable 3 is equal to M into Fc, that is 18.42 Newton per mm square, and loss in cable 2 is also same value, 18.42 Newton per mm square, and loss in cable 1, okay, is equal to M into Fc, that is 18.42 Newton per mm square. Okay, the meaning is there will be loss in the previous cable after each the successive cable being pulled and anchored. That is the meaning. Okay, finally loss in each cable will be given, will be calculated as loss in each cable is calculated as in cable 1. Okay, see, after the cable 1, cable 2 is pulled and anchored, cable 3 is pulled and anchored, cable 4 is pulled and anchored. Okay, after each successive cables being pulled and anchored, there will be loss in cable 1. Okay, therefore it is sum of all the values. Okay, sum of all these 4 values. Okay, that is 0 plus 18.42 plus 18.42 plus 18.42. The answer is 55.26 Newton per mm square. Okay, now in cable 2, after the cable 2, cable 3 and 4 are there. Okay, after the cable 2, cable 3 and 4 are there. So this loss in cable 2 is calculated as sum of these 3 values. Okay, that is 0 plus 18.42 plus 18.42. It is 36.84 Newton per mm square. Okay, sorry, loss in cable 2. Then loss in cable 3. Okay, loss in cable 3. If you want to calculate, see after the cable 3, we have cable 4. So we need to calculate the sum of these two values. So 0 plus 18.42. 0 plus 18.42. That is 18.42 Newton per mm square. Then for cable 4, it is stretched at the last, correct? It is stretched at the last. After this, there is no cable and there is no stretching. So it will be 0. It will be 0. Okay. But now by knowing the loss of pre-stress in each cable due to elastic shortening, finally we have to calculate average loss of pre-stress. Okay. Therefore, average loss of pre-stress due to elastic deformation is equal to average of all the values, that is 55.26 plus 36.84 plus 18.42 plus 0 whole divided by 4. Okay, if you calculate the average, check the answer. It is 27.63 Newton per mm square. Okay, so to this loss of pre-stress, calculation of loss of pre-stress due to elastic shortening is over. Okay, any doubts you can ask students. Okay, now in the next step we will calculate loss due to shrinkage. Second one, loss due to shrinkage. Second one, B, loss due to shrinkage. Loss due to shrinkage. Okay. Total total 6 losses will come in post tension concrete beam. See here, loss due to elastic deformation. Second one is loss due to shrinkage. Third is loss due to creep, relaxation, then friction. All the things we need to calculate. Loss due to shrinkage. For calculating loss due to shrinkage, is given shrinkage strain in concrete. Okay, 2 into 10 power minus 4. Let us see the formula for calculating the loss due to shrinkage. What is the formula? Loss due to shrinkage. It is shrinkage strain into ES. Shrinkage strain into ES. Loss is calculated as shrinkage strain into ES. The shrinkage strain is denoted by epsilon CS. Okay. Shrinkage strain is given in the problem. How much it is given? It is given as 2 into 10 power minus 4. 2 into 10 power minus 4 and Young's modulus of steel. Is it given? Young's modulus of steel, it is not given. Okay, you need to remember, if it is not given, you need to remember this that value. I hope everyone is remembering that value, 2 into 10 power 5 Newton per mm square. So shrinkage strain is given as 2 into 10 power minus 4. Okay, into Young's modulus of steel is 2 into 10 power 5 Newton per mm square. Therefore, loss due to shrinkage is 40 Newton per mm square. Answer is 40. Check the answer. Okay. Now we have calculated loss due to shrinkage. Next is loss due to creep. We'll calculate. C, loss due to creep. Loss due to creep. Third one. For calculating loss due to creep, the formula is so in this problem, which constant is given? Just see. Ultimate creep strain is given. Okay. Ultimate creep strain is given means you need to use the second formula to calculate the loss due to creep. Okay. Epsilon CS into FC into ES. Ultimate creep strain. Using ultimate creep strain formula. Using ultimate creep strain formula. The loss is calculated as, what is the formula? Epsilon CS FC into ES. Ultimate creep strain. Ultimate creep strain. It is given in the problem. How much it is given? Ultimate creep strain. It is given as 4 into 10 power minus 6. 4 into 10 power minus 6. Then FC. Just before we have calculated how much we got, it is FC is 3.07 Newton per mm square. And Young's modulus of steel is 2 into 10 power 5. ES is equal to 2 into 10 power 5 Newton per mm square. Therefore, loss is equal to 4 into 10 power minus 6 into 3.07 into 2 into 10 power 5. By this we get loss due to creep. It is 2.46 Newton per mm square. 2.46 Newton per mm square. Okay. Now we have calculated three different type of losses. That is loss due to elastic shortening, loss due to shrinkage, loss due to creep. We have calculated. Okay, what are the remaining losses? What are the remaining losses? Loss due to relaxation of stress in steel is there. Okay, but in the problem there is lack of data with respect to relaxation of stress in the steel. Percentage relaxation of stress is not given in the problem, correct? Huh? So if it is not given, we cannot calculate. You leave that particular loss. Then what else is remaining? Loss due to relaxation. The percentage relaxation is of steel is not given, so leave that. Then one more loss is there, that is loss due to anchorage slip. Okay, with respect to loss due to anchorage slip also there is insufficient data. Okay, the slip at the anchorage is not given, correct? In the previous problem it was given, we have calculated, but in this problem slip at the anchorage is not given. Leave. Okay, leave that also. Then loss due to friction. Okay, for calculating loss due to friction we need a coefficient of friction, that is also not given here, correct? Coefficient of friction is also not given. So so using the data which is given in the problem, we can calculate only these three losses: loss due to elastic deformation and shrinkage and the creep. Okay, now you calculate the total loss. Therefore, the total loss Okay, therefore the total loss is equal to 27.63 plus 40 plus 2.46. 27.63 plus 40 plus 2.46 is equal to 70.10 Newton per mm square. Okay, therefore the percentage loss you can calculate. Percentage loss is equal to total loss of pre-stress, total loss divided by initial pre-stress into 100. The total loss is 70.10 divided by initial pre-stress is how much? Initial pre-stress it is 950. Okay, 950 Newton per mm square divided by 950 into 100. 950 into 100. Okay, so you'll get percentage of loss as, if you calculate, it is 7.37%. Please cross check the answer. So to this this problem is over. If you have any doubts at any point of calculation, you can ask. Okay. Students, to this I'll end the class and I'll continue in the next class. Thank you.